Hello everybody and welcome to Climate Change Day 18. The last time we were together we looked at the geological history of the Earth and finished our time in this class where we're going to be looking backwards. Today we start looking forwards as we learn about contemporary trends in climate. Come on along. Our quote for today comes from the Prime Minister of the Bahamas, Hubert Minnis, who says, "The small island countries are on the front line of being swallowed into an abyss, created initially by human activity and increasingly by inaction. Our vulnerabilities as states on the front lines are profound." By the end of today, you will be able to explain what is currently changing with temperature and precipitation. Oftentimes when we hear people talking about climate change, the first thing we think about is temperature rise. And this might be because we used to talk about it just as global warming, or because we often hear about trying to keep the warming of Earth to only 1.5 or 2 degrees Celsius. But that's not what we actually care about the most. What we actually care about the most is an increase in heat. And we care about that because heat can do kind of three things for us. One is it can melt ice, which has dramatic impacts, which we've already discussed in here. Two, it can increase temperature, which is what we think about the most. And three, it changes precipitation patterns, which can cause more or bigger storms. So if we look at heat, and we're measuring heat in joules, right? Not in degrees, but we look at the heat in the oceans, we can see that the amount of heat in oceans has risen dramatically over the last 50 or 60 years. And there's more increase in heat in surface waters, which makes sense because those are the places that are able to be warmed directly. And that is the heat that can go into creating increased evaporation and increased strengths of storms. Most of the scenarios of abrupt climate change are not necessarily directly related to temperature. They are much more so related to phase changes. If we melt ice, does this change albedo quickly? If we melt ice, does that change the amount of fresh water in the ocean? How does that impact our ocean currents? If we melt permafrost, is there a release of methane gas that had been stored? If we increase evaporation, are we going to increase droughts and floods? These are the things we should care about the most. You should have learned in chemistry that it takes an incredibly large amount of energy to change the phase of a substance. And while evaporation and condensation are happening more now than they did in the past, they are still happening at the same rate as each other. And so there is no net energy absorption or release by evaporation and condensation. It takes 2,500 joules to evaporate 1 gram of water, but you get that 2,500 joules back every time you condense that gram of water. And so all this evaporation and condensation does with heat is it moves it around. We're moving heat from being in the ocean into the atmosphere. Unlike evaporation and condensation, melting and freezing are not happening at the same rate as each other. There is more melting occurring than freezing. We are melting more glaciers than forming new ones. And as a result, we get a heat sink. It takes energy to melt ice. So when ice melts, we are pulling in that energy, and we're never giving that energy out. A lot of our popular discussions around melting glaciers usually talk about sea level rise, but of course sea level rise is not the only concern. Once the ice is gone and you are no longer able to melt more of it, you lose that heat sink, and that heat must now go somewhere else. When we get together, I'm going to break you up into groups and I want you to answer the following questions. How much energy would it take to melt all of the ice trapped in glaciers? I've given you the volume of glacial ice and the latent heat of fusion for water. Once that's done, all of that energy has to go somewhere. It can go into the air, it can go into the ocean, and it can go into the increased number or severity of storms. If you go stand in the middle of Antarctica in the winter, you are probably not going to be able to see any impact of melting ice. If you want to see changes in systems, it's best to look at their edges. And that's true for glaciers, and that's true elsewhere in life. So if we want to see the impact of this melting, we should take a look at the edges of glaciers. Looking at Muir Glacier in Alaska from 1941 and 2004, we see an incredible difference. There is much more ice here in 1941 than there is in the same place in 2004. And in order for that ice to melt, it had to absorb an incredible amount of energy. Now that that ice is gone, it is no longer available to act as a heat sink. And this is true for other glaciers as well.
All the glaciers are shrinking. In the 1800s, there were estimated to be about 150 glaciers here. However, today we only have 25 glaciers. The glaciers are measured by a number of different ways. One of the most obvious ones is using repeat photography, where we go and occupy a site from which a photographer took a picture in, say, 1910, and then we re-photograph that from exactly the same spot. Once you go every several years to 5 years or 10 years, that's when you see the really big changes. When we first started this project, we thought every other year was going to be too much. But recently we've seen so much glacier change that now we are increasing our frequency of repeating photographs or visiting glaciers. You can see that it's all melted away. The lake has gotten bigger. All this ice has contributed to the water and is retreated back up towards the head wall of the mountain. We also do things that are a little bit more modern, such as taking precision global positioning systems and going along the margins of the ice so that we can look at changes in the area of the ice through time.
Glacier National Park is an excellent natural laboratory to examine the effects of climate change. This area is actually warming at 2 to 3 times the rate of the global average rise in air temperatures. So these increased air temperatures are decreasing the snowpack in the glaciers in the high country and increasing disturbance events like wildfires that we're experiencing.
Some of the species that we're studying, these aquatic insects, might be the first species actually to go extinct due to the effects of global climate change. We've already seen a contraction in the distribution of some of these species in comparison to collections that were done back in the 1960s.
Even though glaciers may seem disconnected and far away to people, they actually affect a lot of things downstream. And that's even evident in other things such as the way that the snowpack affects the huckleberry crop. And this is, of course, a vital food source for grizzly bears.
Animals that live in these upper elevations are adapted to the colder temperatures there, and because we're predicting warmer temperatures, they may be particularly vulnerable to these changes. They also have very specific food needs, and the food changes for them could also influence their ability to thrive.
In spite of the fact that it'll be different in the future, it's still going to be a valuable asset to Americans, both as a research outdoor laboratory and maybe as a kind of iconic lesson as to what climate change can do to natural landscapes.
So hopefully with that, we're seeing that the impact of melting glaciers, in this case alpine glaciers, is not limited just to heat absorption or their beauty, but it also has to do with water availability and food availability and temperatures and ecosystem stability. We've looked at heat absorption by ice. Now let's look at what happens if you have excess energy that does not end up going into a change in phase. This energy gets trapped in the atmosphere, and when you trap energy in the atmosphere, it ends up increasing surface temperature. And we've already gone through this. You know that the average surface temperature of Earth has increased since the Industrial Revolution. If we take the 20th century average temperature for each month and subtract the current month from that average, we can look back and we can see that the last time that we had a month of below 20th century average global surface temperatures was in 1985. So that means that if you were born after 1985, and since you're in high school you were, and since I'm not that old yet, I was, we have never lived in a month that had below average temperatures. Every month of our lives, the world has been above the 20th century average. You can see the changes at the edge. Just like with the glaciers, if you stand in the middle of a climate zone, you're probably not going to notice that much of a difference. But our climate zones are moving. It is getting warmer farther north. It is getting warmer higher up mountains. If you're standing on the edge of a climate zone, you might find yourself in a different zone than you were when you were born. I was born in 1990, and if we look at 1990, we can see that I was born just outside of Detroit, and I was in zone 5B, which means that the average annual lowest temperature was somewhere between -10 and -15 degrees. Now, I don't live in the Detroit area anymore, but my parents still do, and they are no longer in that same climate zone. It does not get as cold there as it did in 1990. And that has an impact on what plants they can grow in their yard. If we look not in somebody's yard, but in a natural system, that impacts what plants are able to grow. We're seeing movement north of trees. You can go farther north and you can still see maples now. Birch trees, they need the cold. They are not found as far south. These changes are happening. You're seeing the animals move, and plants are moving as well. The only question is whether or not plants are going to be able to move fast enough to keep up with it, or whether or not animals are going to run out of room, either going north or going up in elevation. If we look at the Keeling curve, our amplitude has increased. Every year we know that we're getting the up and down movement of carbon dioxide in the atmosphere, and the amount that goes up and down has increased 20% in Hawaii and 40% in the far north. And so we are seeing changes in these patterns. We are also seeing the shifting of when the values start to decrease in the spring and summer because we are moving our start of spring dates up. Continuing on with global patterns in precipitation. There are places on Earth where the precipitation has not changed all that terribly much. But you're going to find that those are in the minority. Areas that were dry are getting drier. Areas that were wet are getting wetter. This is because the increase in Earth's energy is causing that increased evaporation and precipitation. Not only are places getting more rain or less rain, but the rain that is coming is arriving in fewer but more intense events. And so even if you're in a location that has increased rainfall, you might see fewer days of rain. But when the rain does come, you get a lot of it, and that causes flooding. For agriculture, to grow crops, it's better to have rain spread out evenly over the growing season. However, even in areas that are getting more rain, we're seeing fewer events. And so you see areas get really dry and then flood, and then dry out and then flood. And that is not good for crop production and food security. Taking a look at the other side of the world, this is happening as well. The deserts of the world are expanding. There are many causes to this. You've got deforestation, overgrazing, and climate change. And because of the climate change, if you have a disturbance, areas that historically would have been able to recover are now not recovering but are instead transitioning to desert.
We always had plenty of rain, says Saidu Sawadogo, a common farmer. Harvests were sufficient. Back then, everything was green. There was forest around the villages. Now, there is only sand. My land is not nearly as fertile as it used to be, he laments. My storage shed is almost empty already, says the farmer. Pretty soon we're going to have to buy millet ourselves, but the price keeps going up. A year ago, 100 kilos cost 35 euros. Now, it's at 55 euros already. I can't afford it, only if my brother sends me money. His brother has been working as a farmhand, harvesting crops in the neighboring country of Ivory Coast for 15 years. 17 people used to live on the family farm. Now only 5 people who can work remain, along with Saidu's 78-year-old father. His brother's sons recently moved to Ivory Coast too, during the current drought. It is out of the question for me, says Sayadu. I have to stay here. The younger ones can leave or work in the gold mines in this area, like my wife and children already do. Sayadu does not understand the exact meaning of climate change, but this much he does understand. Something is changing, and it's not good for us. Climate change is caused above all by the general warming, explains climate expert Isidore Zonga from Ouagadougou. From the 1960s to the present, we've recorded a rise in temperature of about 1.7 degrees. Greenhouse gases are to blame for this. Farmer Sommet Claude has been recording the exact rainfall in a notebook since 1999. Perhaps not to scientific standards, but as someone directly affected by these changes. I began keeping these notes so that I could predict when the rain would come and when I could start sowing my crops. But these notes have also shown me how things are changing. If you compare 2010 to 2011, for instance, one year it rained heavily for 5 days and then not at all for many days. Rural populations suffer disproportionately from weak and erratic rainfall. In a country like Burkina Faso, this includes almost 80% of the inhabitants. Poor harvests have created a state of chronic food insecurity in the country. Moreover, the groundwater level is sinking by approximately 0.5 to 2 meters per year in the Sahel zone. As a consequence, if a farmer digs a well, it runs dry within 5 years. Farmer Prosper Sawadogu is already employing modern rehabilitation techniques, such as stone belts and tree planting, but he is not making any headway in a struggle against a sinking water level. Water simply remains scarce. There's no river here, says Prosper, only a little spring. Watering the trees is crucial. Some need watering every day, others just once a month. I actually have to buy water. But the trees and the stone belt help me. Without them, the rain would just wash the soil away. We don't just show the farmers how to set up stone belts or plant trees, we supervise their efforts until the trees are strong enough. Tree survival rate is 77%, quite a success. Some of the trees bear fruit, guaranteeing the farmers a second source of income. Alongside global warming, local deforestation has played a role in desertification, says Isidore Zonga. The farmers themselves are responsible for this, but poverty forces them to chop trees for firewood. Some farmers even slash and burn areas of the forest to expand their acreage because the available ground has been depleted. People cut down trees without replanting, says farmer Prosper Sawadogu. If I hadn't started to plant trees myself years ago, we couldn't sit here in the shade right now, and my farm would already have been washed away by the rain. My harvests have suffered from the current drought too, but compared to other farmers with no trees and stone belts, I'm prospering.
So let's move over from Burkina Faso over to Chad and take a look at what's going on in that neighboring country.
Early morning in Lake Chad, Musa Adam, like his father and grandfather before him, earns a living as a fisherman. For centuries, the lake's waters have been a rich source of food and water for the people living on its shores. 10 years ago, a catch as little as this would have been thrown back, but not anymore. Fish are now so scarce that every single one, however tiny, will be shared out in the village.
We give each person one fish, but the problem is what happens when there are no fish. No fish means no food and no jobs.
From the air, the fisherman's problem is clear to see. What was once one of the world's largest lakes is now a patchwork of weeds, ponds, and islands. Images from space show how a huge body of water 50 years ago is now just a 20th of that size. A combination of recurrent droughts and temperatures of up to 50 degrees Celsius is the root of the problem. The lake is now just 7 meters at its deepest. And land that was once fertile has turned dusty and barren. For communities living on the lake's edge, the effects are devastating.
At first, we didn't know anything about malnutrition, but now there are huge numbers of malnourished people. The children are all malnourished. There are no more fish, there's no more milk, no maize, vegetables, or cereal.
At the nearby clinic, there's further evidence of the problem. Weighing just 7 kilos, 5-year-old Fatima is less than half the weight of a healthy child her age.
When Fatima came here, she didn't speak. She was always lying down with empty eyes. Now she's asking for water and food, asking to wash her or to dress her. So now we've got hope.
Where food is being grown, it's in irrigated fields. But overuse of water is also contributing to the lake's shrinking size. At its current rate of decline, the lake could be gone within 20 years. There has even been talk of diverting the region's rivers to refill it. Official figures show that more than 20 million people depend on these waters.
If there are solutions, we must find them. For every problem, there is a solution. The lake is in the process of disappearing, and the lake feeds many people, not just here, but also for people in other countries living near the lake, like Nigeria, Cameroon, and Niger.
Local community groups, meanwhile, are trying to halt the erosion by planting trees along its shores.
I was born here, I grew up here, and I want the lake to come back, not just for me, but for the children of the future. To stop the Sahara, we must put in extra effort. Every day and every night we must work.
Reforestation programs are slow, and Lake Chad is drying up fast. So far, no alternative solution can be found. Villagers' determination at least offers hope to the communities who call this region their home.
It's now time to look at that third effect of increased heat that we talked about at the beginning of class, which is bigger and more storms. And we're going to focus in on tropical cyclones. So these are hurricanes and typhoons. And what these are is they're strong, low-pressure storm systems that form in the tropics. They've got rotating winds, a central eye, and heavy rain. You all know that because you've seen the devastation that these have caused from watching the news. And these are just an example of a Carnot heat engine. Hurricanes bring wind, rain, and storm surge. I want to take a look down here so we can get kind of an example of what that storm surge is. So we've got wind-driven surge and pressure-driven surge. Because a hurricane is such a low-pressure system, there's less atmosphere pushing down the water, and because there's higher pressure surrounding it pushing down, that causes the water to rise up in the middle. And so you end up getting a surge from pressure of water levels that are higher than you could be expected. You also get wind-driven surge, so we've got the wind blowing, just like the wind blows the water across the Pacific, which causing a buildup of water in the west when La Nina occurs, we get the same effect but on a smaller scale during a hurricane. And the larger these surges are, the more flooding that gets brought in with the hurricane. Warmer water contains more energy to power these tropical cyclones. You take that and couple it with higher sea levels, and that makes it easier for the storm surge, which is extra high itself, to reach cities. As we look at how climate change impacts hurricanes, I want you to take a look at these two figures. And so we can see that over time, so from the 70s up to the early 2000s, we've seen an increase in the absolute number of Category 4 and Category 5 storms. We have, though, during that time, seen a decrease in Category 1 storms. And that's not true just for absolute numbers, but also for percentages. The percent of storms that are strong has increased. Let's take a look at the changes in percentages of hurricanes that are Category 4 and Category 5 over time. If we look in the Eastern Pacific, Category 4 and Category 5 storms accounted for 25% of hurricanes in the 70s and 80s. But in the 90s and 2000s, they accounted for 35%. In the South Indian Ocean, they accounted for 18% before and 34% now. And that increase has occurred in all of our ocean basins. The storms appear to be getting stronger. You've probably heard, well, of course, the hurricanes are getting stronger because there's this about 30-year cycle in North Atlantic sea surface temperatures, that 30-year cycle of hurricanes. And therefore, more Atlantic hurricanes should occur in the warm phase. That makes sense. We've been in the warm phase since 1999, and therefore, we should expect to be seeing more stronger storms. Has this increase in storms been the result of climate change or Atlantic multi-decadal oscillation? To answer that, we have to look at the number of hurricanes and their strength at a global level. AMO impacts Atlantic hurricanes, but Pacific typhoons have increased during this time period as well. That tells us that the increase in strength of storms is not just due to AMO. Climate change makes hurricanes more powerful, but does not necessarily increase their frequency. While we saw in our graph earlier the number of Category 4 and Category 5 storms increasing, we saw a decrease in Category 1 and Category 2 storms. Over time, we can actually expect that the number of storms themselves might actually go down. We cannot say that climate change caused a particular hurricane or other event to occur. People often ask, was this storm caused by climate change, or was this heat wave caused by climate change? No. Climate change did not necessarily cause a hurricane to occur. But we can say that climate change makes the hurricanes that do occur worse. When you have higher sea levels, you get more storm surge. That directly increases their impact. When you have warmer water, hurricanes get stronger. Adding half a degree Celsius increases wind speeds in hurricanes 15 to 20 miles an hour. If you are interested in looking at how climate change impacted specific events in the past, these are two really good resources for you to check out. Today was a lot. We've seen a lot of the effects that climate change is having today. Take a deep breath, come to class, and we'll talk about some of those impacts in more detail. We'll see you later. Bye-bye, everyone.